Alright, let's go. Number 12. The Little Red Dots. In 2022, Evo Lab's team at Swinburne University of Technology was doing something routine. They were counting galaxies. JWST had just come online, and the first deep near-infrared images from the Sears survey needed a census. How many objects, how bright, how far. Standard catalog work, the kind of task you hand to a postdoc. The standard model of galaxy formation makes a firm prediction here. In the first 500 to 700 million years after the Big Bang, there simply has not been enough time. Gas has to cool, collapse, form stars, merge, and repeat. Galaxies at that epoch should be small, blue, ragged, and light, perhaps 100 million solar masses. Growth is slow because gravity is slow. The images came back full of compact red points, tiny, impossibly heavy. Lab and colleagues published in Nature in February 2023 describing 6 objects at redshifts between 7.4 and 9.1, with inferred stellar masses reaching 10 to the 11 solar masses, a Milky Way's worth of stars assembled in under 700 million years. Then Koos Boogd at the Center for Astrophysics found UHZ-1 in 2023, a black hole of roughly 40 million solar masses at redshift 10.3. Every escape route was tried. Dust reddening. Spectroscopy confirmed the redshifts. Photometric error. The follow-up held. Perhaps they are not stars at all, but accreting black holes, which would fix the mass problem for the galaxies. It relocates the crisis into the black holes, which are then too massive to have grown from stellar seeds. A top-heavy initial mass function was proposed. Feedback-free starbursts were proposed. None of them explains the population, only individual members of it. We built a telescope specifically to confirm our picture of cosmic dawn. It returned data that the picture does not permit. If the first galaxies assembled that fast, then the history that produced the atoms in your hand did not happen the way we have been telling it. The next entry does not break a model. It breaks the assumption underneath every model. Number 11. The Big Ring and the Giant Arc. Alexia Lopez, a PhD student at the University of Central Lancashire working with Roger Klaus, was mapping magnesium absorption lines. Distant quasars shine through intervening gas. That gas leaves a magnesium-2 fingerprint in the spectrum. Trace enough fingerprints and you can map matter that emits no light of its own. It is careful, unglamorous cartography. Cosmology rests on the cosmological principle. On large enough scales, the universe is smooth and looks the same in every direction. Yadav and colleagues calculated in 2010 that this smoothness sets in at roughly 370 megaparsecs, about 1.2 billion light-years. Nothing coherent should exceed it. That number is not decoration. It is the license to use the equations at all. Lopez found a crescent 3.3 billion light-years long. She announced the giant arc at the American Astronomical Society meeting in June 2021, with a statistical significance of 5.2 sigma. In January 2024, she announced a second structure in the same sky region and at the same redshift of about 0.8, the Big Ring, 1.3 billion light-years in diameter and roughly 4 billion light-years around. 2 structures. 1 neighborhood. Both illegal. The failure parade is long. Chance alignment, the significance rules it out at the level cosmologists normally accept as discovery. Selection bias in magnesium-2 absorbers, the same technique reproduces known structures correctly elsewhere. Projection, 2 unrelated sheets seen edge-on, the redshifts match too tightly. And these are not isolated. Klaus found the huge large quasar group in 2013 at 4 billion light-years. Horth reported the Hercules, Corona Borealis Great Wall, at nearly 10 billion. Each time, the response has been to question the statistics rather than the principle. The cosmological principle is the assumption that makes cosmology a science rather than a description of one particular viewpoint. Ours, if the universe is not smooth, then every distance you have ever been told, including how far away tomorrow's sky is, was calculated with the wrong ruler. The next object does not violate a limit. It violates an absence. Number 10. NGC 1052 DF2. Peter Van Dokkum's group at Yale was hunting ultra-diffuse galaxies, enormous, faint, ghostly systems that had only recently been recognized as a class. The Dragonfly telephoto array was built for exactly this: cheap telephoto lenses ganged together to catch surface brightness too low for conventional mirrors. They wanted a catalog. They wanted statistics. Every galaxy ever weighed has come out heavier than it looks. Rotation curves stay flat where they should fall. Velocity dispersions run high. The standard interpretation is dark matter, typically 10 to 100 times the visible mass in a halo around each galaxy. Under MOND, the alternative, there is no halo. Gravity itself changes behavior below a critical acceleration. Either way, the excess is mandatory. It is not optional in any theory. DF2 came out weighing exactly what its stars weigh. Van Dokkum published in Nature in March 2018. 10 globular clusters gave a velocity dispersion so low the team could only quote an upper bound of 10.5 kilometers per second at 90% confidence. Shani Danieli's 2019 follow-up with the Keck Cosmic Web Imager measured the stellar dispersion at 8.5 kilometers per second. The mass-to-light ratio came out near 2. That is stars. Only stars. Objections arrived immediately. Trujillo's group argued the distance was 13 megaparsecs rather than 20, which would restore the missing mass. Van Dokkum's tip of the red giant branch measurement put it at 18.7. Tidal stripping was proposed, but the galaxy shows no tidal tails. Pavel Krupa argued the MOND external field effect from nearby NGC SIN 1052 suppresses the boost, which requires the galaxy to sit at a very particular distance and orientation. Then DF4 turned up. Then a trail of them. Here is the inversion. A galaxy without dark matter is a problem for MOND, because you cannot switch a law of gravity off in one place. The absence is evidence for the substance. The stuff that outweighs you by a factor of 5 in your own galaxy can, apparently, be left behind somewhere. The next object should have gone silent decades before it was found. Number 9. GPM J183990. Natasha Hurley Walker at Curtin University was running a survey for transients, the Murchison Wide Field Array sweeping low-frequency radio sky for anything that flickers. Her team had already found one oddity in 2022, an 18-minute pulsar that had switched off. They were looking for more of the same. Routine follow-up on an anomaly they assumed was a one-off. Neutron stars work by rotation. The spin drags a magnetic field, the field accelerates particles, the particles cascade into pairs, and the pairs radiate. Spin down far enough and the voltage drops below the threshold for pair production. This boundary is called the death line, and it sits at periods of roughly 12 seconds. Slower than that, and the radio emission is supposed to shut off permanently. This object pulses every 1,318 seconds. 22 minutes. Hurley Walker published in Nature in July 2023. The pulses run between 30 and 300 seconds long. When the team went into archival data, they found the source in observations dating to 1988, 35 years of continuous activity, far past the death line, with no measurable sign of stopping. Explanations were offered in sequence. A magnetar with an exotic field geometry, but magnetars burn out on timescales of thousands of years, and this one shows no spin down. A white dwarf pulsar, which would permit the long period naturally, no optical counterpart has been found where one should be. A binary system mimicking a single rotator, the timing is too clean. An entirely new class of object with an unknown power source, which is not an explanation, only a name for the gap. Something out there is generating a coherent radio beam using a mechanism that our physics says does not exist. Every model of stellar death we teach has this object sitting outside it, still transmitting. The next entry is not one object. It is a category we could not see until 6 years ago. Number 8. The odd radio circles. Ray Norris and the EMU team at CERO were commissioning hardware. The Australian Square Kilometra Array Pathfinder had just come online in 2019, and pilot surveys exist to check that the instrument behaves. that the calibration holds, that the noise is where it should be, that known sources appear where the catalogs say. Nobody expects discovery from a commissioning run. Radio sky is well characterized. Extended emission comes from supernova remnants, from planetary nebulae, from the jets and lobes of active galaxies, and from clusters. Every one of these has a signature morphology and a counterpart at other wavelengths. A structure with no optical, infrared, or X-ray counterpart is, by long convention, an imaging artifact. They found rings. Perfect ones. Nothing at any other wavelength. Norris published in Publications of the Astronomical Society of Australia in 2021. The first confirmed odd radio circle sits at redshift 0, 55, which makes it roughly 1 million light-years across, larger than the Milky Way's disk, with an elliptical galaxy sitting precisely at the center. Meerkat imaged them in higher resolution in 2022. Fewer than a dozen are confirmed. Artifact, ruled out by independent instruments. Supernova remnants, far too large and at the wrong galactic latitude. End on radio galaxies, the central galaxies are not active. Gravitational lens rings, no lensing geometry present. Alison Coyle's team published in Nature in 2024 finding outflowing gas in the host of ORC-4, supporting a starburst-driven shockwave model. It requires an outburst of a scale nobody has observed directly, and it does not yet account for the full population. They are only visible in radio. Before 2020, we did not have the sensitivity. The sky above you may be full of million light-year structures that no human eye or telescope has ever registered. The next entry is not violent. It is the coldest place in existence. Number 7. The Boomerang Nebula. Raghvendra Sahai at NASA's Jet Propulsion Laboratory and Lars Kahneman were conducting a survey of carbon monoxide emission around dying stars. Post-asymptotic giant branch objects, stars in the brief window between shedding their outer layers and igniting as planetary nebulae. The point was to measure outflow speeds across a sample. Bookkeeping for stellar death. There is a floor to temperature in this universe. The cosmic microwave background sits at 2.725 Kelvin, and it fills all of space. Any object left alone will equilibrate to it. You cannot passively be colder than the background. In the same way, you cannot passively be colder than the room you are sitting in. Below 2.725 Kelvin, nothing should exist naturally. The carbon monoxide showed up in absorption against the background. That only happens if the gas is colder than the thing behind it. Sahai and Nyman published in Astrophysical Journal Letters in 1997, measuring roughly 1 Kelvin, minus 272 degrees Celsius. The mechanism is adiabatic expansion. Gas rushing outward at 164 kilometers per second does work against nothing and cools below the floor. ALMA confirmed the structure in 2013. The cooling is understood. The engine is not. The central star is losing mass at a rate roughly 100 times higher than comparable objects, and has sustained it for around 1,500 years. Single-star models cannot produce it. A binary companion spiraling into the envelope is the leading candidate, and no companion has been detected. Magnetic launching has been proposed. Dust-driven acceleration falls short by an order of magnitude. The universe generated something colder than the residual heat of its own beginning, and it did so by accident, while a star was dying. Every atom in your body is warmer than the coldest thing in the universe, and it took a star tearing itself apart to go lower. The next entries are not sitting still. They are leaving. Number 6. The Hypervelocity Stars. Warren Brown at the Smithsonian Astrophysical Observatory was surveying the outer halo for blue horizontal branch stars, tracers used to map the shape of the galaxy's gravitational field. It is a mapping exercise. You measure radial velocities on hundreds of faint blue stars and look for structure in the distribution. The Milky Way's escape velocity in the solar neighborhood is roughly 550 kilometers per second. Stars in the disk orbit at about 220. Halo stars move faster and on wilder orbits, but they remain bound. The galaxy holds on to everything it makes. A star exceeding escape velocity has no ordinary way to acquire that energy, because supernova kicks in binaries top out well below it. One star in his sample was moving at 709 kilometers per second. Brown published in Astrophysical Journal Letters in 2005. The mechanism had been predicted by Jack Hills in Nature in 1988. A binary pair wanders too close to Sagittarius A star. The black hole captures one member, and the other is flung out with the binding energy of the pair. In 2019, Sergei Kopasov and the S5 collaboration reported S5 HVS1 at 1,755 kilometers per second, traced back to the galactic center with an ejection date about 4.8 million years ago. Not all of them fit. US 708 moves at roughly 1,200 kilometers per second, and its trajectory does not pass through the center, pointing instead to a thermonuclear supernova in a tight binary. Some candidates trace back to the Large Magellanic Cloud. Others have no traceable origin at all, which leaves either an unknown massive black hole somewhere in the disk or a mechanism we have not written down. Some of these stars may have carried planets with them. There are worlds in permanent intergalactic darkness right now, thrown out of a galaxy, and nothing about their physics forbids life having started on them first. The next entry is not an object out there. It is where we are. Number 5. The KBC Void. Ryan Keenan, Amy Barger, and Lennox Cowie at the University of Hawaii were building a near-infrared galaxy count. Infrared traces stellar mass more reliably than optical light. So the aim was a clean measurement of how galaxy density behaves with distance, a calibration exercise for everything downstream. The cosmological principle again. Beyond a few hundred megaparsecs, density should converge to the cosmic mean. Local variations exist, but they should be small and they should wash out quickly. Where you happen to stand should not matter. Density did not converge. It rose steadily out to enormous distance. Their 2013 paper in the Astrophysical Journal reported evidence for an underdensity roughly 300 megaparsecs in radius, about 1 billion light-years, with the local region running around 20% below the cosmic average. We appear to be near the center of the largest known void in the observable universe. The consequence is severe. Inside a void, matter falls outward toward the denser walls, and local expansion measured from inside would read faster than the true global rate. That is the Hubble tension exactly. Ben Hoscheit and Barger explored this in 2017. Then Kenworthy, Skolnick, and Rios showed in 2019 that the void would have to be deeper and larger than observed to close the full gap. And CDM itself does not comfortably produce voids this big. Simulations make them rare, at the edge of what the model permits. Either the greatest crisis in modern cosmology is a parallax error caused by our address, or our address is one the model says should not exist. Every number you have ever heard about the age and fate of the universe may have been measured from inside a blind spot. The next entry means our galaxy may not have one center. Number 4. The wandering supermassive black holes. Angelo Ricart, Michael Tremmel, Priyamvada Natarajan, and Thomas Quinn were running cosmological simulations, the Romulus suite, to study how supermassive black holes settle after galaxies merge. The question was mundane. How long does it take two central black holes to sync together and coalesce? It matters for gravitational wave predictions. The textbook picture is one supermassive black hole per galaxy, parked at the dynamical center. Mergers deliver a second, dynamical friction drags it inward, the pair spirals in, and the system returns to one. Order is restored on timescales short compared to the age of the universe. In the simulations, they frequently did not sync. Ricart and colleagues published in monthly notices of the Royal Astronomical Society in 2021. A Milky Way mass galaxy should host on the order of 12 wandering supermassive black holes, off-center, bound to the halo, but not to the nucleus. Observation supports the mechanism. Marco Kyaberg reported in 2017 that the quasar 3C186 sits offset from its host galaxy, apparently recoiling at roughly 2,140 kilometers per second after a merger, kicked out by asymmetric gravitational wave emission. Finding them is the problem. A black hole that is not accreting emits nothing. Microlensing searches are ongoing and have not been decisive. Stellar dynamics can reveal them only if they sit inside a dense enough cluster. Hypervelocity star trajectories that do not trace to the galactic center are one of the few indirect hints, and they are ambiguous. Sources such as ET-LX1 remain contested. Our galaxy may contain a dozen objects of millions of solar masses, and we cannot say where any of them are. There may be one closer to you than Sagittarius A star, and we have no method that would tell us. The next entry says we are moving at 2 different speeds at once. Number 3. The Cosmic Dipole Anomaly. Nathan Sechrist at the United States Naval Observatory was performing a consistency check. Ellis and Baldwin proposed the test in 1984. Because we move relative to the cosmic rest frame, distant sources should appear slightly bunched and brightened in the direction of travel. The dipole in the